Welcome back to Metaphor Math, and we're on to problem 3a in Rosenlicht's Intro to Analysis. And they're asking us to both prove the following statements and illustrate them with diagrams, but I'm going to illustrate the diagram first here, just to motivate our proof. So, in this illustration that I'm about to write is just one possibility of what this could be. Like A and B, for instance, A and B could be disjoint, or A and B could be the same set. It doesn't specify here, but this is just one possibility of what this could look like. So let A be the area inside this pink circle here, and then let's say B is this orange circle here. This is B. And then let's say our set S is just this, which I like to call the overarching set, or the universe, some people call it. And A and B lie in S, or that is, they are subsets of S. And we want to, let's first color in with, let's say green, the complement of A. So the complement of A, or the complement of B. So the complement of A is everything that's not in A. So that would be everything that's not in the pink circle. So I'm just going to maybe color in all this area. And it's also over here. So this counts as not an A. This is in S, but it's not an A. And yeah, there we go. Okay, so that's everything that's not in A, and also we could also have or everything not in B, because union is another way for union is or. Another way to think of a union is or. That is, the word or is you could either be in the complement of A, or you could be in the complement of B, or both. I'll get to that later, but or in mathematics, when we say or in mathematics, we mean or both. So let's say that the complement of B is everything in blue. So that could be everything that's not in B. So everything that's not in B. So everything that's in A and not in B counts. Still in A, but it's not in B. Of course, this couldn't be, even though this is in A, but this is still in B. This area right here, this is in B, so we couldn't color that in. And everything over here, this is in S, but of course still not in B. And there we go. So here, everything that's colored in is not A or not B. And let's see if that's the same as the complement of A intersect B. And of course, this is A intersect B. And we see immediately that the complement of A intersect B is everything that's not in A intersect B, and that's everything that we've colored in. So the illustration, the way we illustrated this kind of fits, or it makes sense, and can possibly motivate our proof here. So let's go on to our proof. And I'm going to erase this. Let me go eraser. There you go. Okay. So here, oopsie. We are doing a good old set equality. And remember, remember that when we do set equalities, oh dear, I'm having some trouble erasing this here. Okay, there we go. Okay, so when we do set equalities, we want to show that the left side is a subset of the right side, and the right side is a subset of the left side. Just like before. So we want to show that first, the complement of A union the complement of B is a subset of the complement of A intersect B, And then the second step is we want to show the other direction, that A, the complement of A intersect B is a subset of the complement of A union the complement of B. But let's do one first. Let's do this direction first, where we show that the complement of A union the complement of B is a subset of the complement of A intersect B. So, if we want to show this, then if we can show that any arbitrary x in here, any arbitrary x in the complement of A union the complement of B, must also be in the complement of A intersect B, if we can show that, then we've shown that every x, because our x was chosen arbitrarily and that lied in this set, the x that we chose that lied in the complement of A union the complement of B was arbitrarily chosen. So if that x must be in the complement of A intersect B, then all x that are in all x's that are in the complement of A union the complement of B must also be in the complement of A intersect B. So let's do that. So let x be, and so we're saying let any x, let some arbitrary x that is in A union, let x be in A, the complement of A union the complement of B. Okay, so we're saying, okay, let's just choose some x in here. And so what does that imply? Let's think about what that implies. That implies that x is in the complement of A, or x is in the complement of B. And let me just emphasize something here. I want to write this in red. Or in when we say or in mathematics, the mathematical or in mathematics means one or the other or both. Or both. Usually when we say or in English, it usually means exclusive, like I'm going to go to the park or I'm going to go to the movies, but not both. We usually don't mean, oh, I'm going to go to the park and to the movies. But in mathematics, it's implied, or the or both is implied. So x could be in the complement of A, or it could be in the complement of B, or it could be both in the complement of A and the complement of B. So that's the first thing. And the second thing is just to remember, this is number one here, and the second thing is just to remember, when we have x being in the complement of some set x, when x is in the complement of x, this sentence doesn't make sense. So when x is in the complement of some set x, just any general set x, then that means that x is not in x. This is an if and only if statement. That means if x is not in if x is not in x, then x must be in the complement of x. And if x is in the complement of x, then that means x must not be in x. And that's because the complement of x is everything that's not in x. So if x is in the set that's everything that's not x, then x must not be in x. And vice versa. If x is not in x, then it must be in the complement of x. So, back to our proof. If x is in the complement of A or x is in the complement of B, then we have case 1. Case 1. X is in the complement of A. But that implies, by our reasoning, right here, the second statement, or not our reasoning, but our remembering, that x is not in A. And that implies that x is not in A intersect B. And why is that the case? Because in order for x to be in A intersect B, it must both be in A and B. But here, we just showed that x is not, if x is in the complement of A, then it's not in A, and it can't possibly be in A intersect B, because in order for it to be in A intersect B, then it must be in both A and B. So that implies, by the same thing here, x is not in A intersect B, which means x is in the complement of A intersect B. And we're going to use the same reasoning for our case 2, which is, as you can imagine, x is in the complement of B. Well, again, that means that x is not in B. And then that means that x can't be in A intersect B. Because in order for it to be in A intersect B, again, it has to be both in A and B. And since A... Oh, I need to put a flash through here. X is not in B. And so since x is not in B, it can't possibly be in A intersect B, because it has to be both in A and B in order for it to be in A intersect B. And since it's not in A intersect B, then it must be in the complement of B, A intersect B. Okay, and you might be wondering, okay, well, what about case 3? And I argue that we don't really need a case 3, because case 3 is, or I'll put that in parentheses, the quote-unquote case 3 is that x is not in x is in the complement of B and x is in the complement of A. So I'll just write it. X is in the complement of A and x is in the complement of B. But as you can see, since x is in the complement of A and x is in the complement of B, then it falls into both case 1 and case 2. Since x is in the complement of A, then all of these implications hold. And since x is in the complement of B, all of these implications hold. So it can't possibly be in A intersect B, so therefore x must be in the complement of A intersect B. So I'll just say this implies by cases 1 and 2 that x is in the complement of A intersect B. Okay, and we're done with this with number 1. We've just shown that x, no matter what, if x is in the complement of A or if x is in the complement of B or both, but I won't say or both anymore because we're going to learn that we need to solidify the fact that the or in mathematics, it's implied that it's implied or both. The or both is implied. But yeah, we just showed that if x is in the complement of A, then it can't possibly be that it's in, or that it is in the complement of A intersect B. And if x is in the complement of B, then x is in the complement of A intersect B. So every x that's in this set, every x that's in the complement of A union the complement of B, must also be in the complement of A intersect B. So let's move on to the second step, which is to show that the complement of A intersect B is a subset of, or is contained in, the complement of A union the complement of B. Let me finish erasing this first. Okay. And all I'm going to do here is I'm just going to erase this here because we're just going to flip that around. We want to show that the complement of A intersect B is a subset of the complement of A union the complement of B. And I also like to think of this sign when it goes backwards like this, or just in general, we can think of this also as the complement of A union the complement of B contains the complement of A intersect B. So onto this. This is part 2 here. Let me write that. So again, we're going to just say that some arbitrary x is in, or we're going to choose an arbitrary x in A intersect B, or the complement of A intersect B, and show that it must also be in the complement of A union the complement of B. So let x be in the complement of A intersect B. Then this means that x is not in A intersect B. And let's think about this. Let's draw a picture again. If x is not in A intersect B, there's just two A's and B's here, and this is A intersect B. If x is not in A intersect B, then it's either in A, or it's either not in B, So it could be over here, or it could be over here. It could be in our general set. This is our overarching set S. So it could be over here, it could be over here. So it's either not in B, or it's not in A, or both. It could be out here, which is neither in A nor in B. And or both, and the or that I vocalized there, that's a kind of a hint as to what we're leaning towards, or what this set might turn out to be. And we know it's going to turn out to be this. I mean, we know that, or in other words, we know that this, any x that's in here must also lie in here, because this equality must hold, because they're telling us to prove these statements. But that or is important, and let's talk about it here. So if x is not in A intersect B, then x is not in A, or x is not in B. Again, or both, because remember, the or in mathematics, it's implied, the or both is implied. So x is not in A, or x is not in B. And remember, if x is not in A, then that means x is in the complement of A, or x is in the complement of B. But look at this. If x is in the complement of A, or x is in the complement of B, that's the same as saying that x is in the union of the complement of A and the complement of B. And we're done. We've just shown that any arbitrary x in A intersect B, the complement of A intersect B, must also be in the complement of A union the complement of B. And we showed the other direction. We showed that any arbitrary x and the complement of A union the complement of B must also be in the complement of A intersect B, therefore showing that they're subsets of each other, and therefore showing that they're equal. The two sets are equal to each other.